Hello and welcome to our first lecture. The natural language of electromagnetism is vector analysis. So our first chapter, chapter 2, deals entirely in vector analysis and the tools that we will need to help us formulate Maxwell's equations, which is the end product of this class, understanding Maxwell's equations, which are the fundamental laws of electricity and magnetism. They are correct. Classically, they are correct with a little tweaking quantum mechanically, and they're just flat out correct in any circumstance in the real world that you can envision. So let's have a look at vector analysis. It's chapter 2. If you have the notes open, that would be great. So we began by what is hopefully a refresher, the representation of a vector. We know a vector is something that has both magnitude and direction, and it is represented by an arrow. And I'm going to only do this in 2 dimensions. I put my X and Y coordinates in standard orientation, that's theta. And we know that if this is the vector A, it has a component here along the x-axis at A cosine theta. And it has a component here, A sine theta. And we also know by the Pythagorean theorem, A is x squared, ax squared plus ay squared, square rooted. And I know that angle, and this is true in 3 dimensions as well, of course, you just have to massage these a little bit. But just for our review today, let's go back to general physics and make sure we're all on the same page, is ay over ax. And as I tell my general physics students, this needs to be plotted because you can get ay over ax to be positive in quadrant 1 or in quadrant 3. Both are positive, both are negative. We know how to add vectors graphically by the tip to tail method. If you have vector A here and vector B here, we can slide A to B or B to A. Either way, it doesn't really matter, but we have to slide, keeping everything in parallel, and our resultant is first tail to last tip. And another way you can see that, maybe more visual, would be to do this and move B there. And of course, in physics, because we're stressing the analytical form of vectors to be able to do computations with precision, we would write A this way in terms of its unit vectors and B this way, which is bx I hat plus by j hat plus bz k hat. And we know vector addition and subtraction is very simple. We do it component by component. All the way here, component by component. And once we're at this stage, if we want the magnitude, we go back to our fundamental definition, use the Pythagorean theorem. So the vector addition and subtraction, of course, should be review if you're sitting in the chair you're sitting now. And we move on to vector multiplication. There are 2 types of vector multiplication. There's called the scalar or dot product. A dot B is AB cosine theta, where theta is defined as the angle as they are, the 2 vectors are situated tail to tail. This is a subtlety not always discussed properly, I think, in some of the texts or sometimes even in lectures. Where's that angle? Is that angle tip over here, tail to tail? That's how you situate them. So wherever they are, you know that you can slide them around and orient them such that they're tail to tail. And we have unit vectors that have magnitude 1 and point in the x direction for the I hat. J hat points along y, and k hat points along z. I would encourage you now, if you have, if it's been a while or you're not quite as familiar with this as you might want to be proceeding, if you have the notes open, you'll find a link in the notes that deal with, it's a Khan Academy video that will help you be refreshed on the ideas behind the dot product. So please take a minute now, go through that video and return if you need to, have a view at that video and return when you're done. And I will pause and we'll take up from there. If you've seen that video, you should be able to make sense of the following chart. Because once we have the unit vectors fleshed out, everything else is easy. So let's have a look at I hat dot I hat. Using my definition that A dot B is AB cosine theta, I'm going to oval it, which is right here. I see that I hat dot I hat, because this has magnitude 1 and this has magnitude 1, will be equal to 1 times 1 times the cosine of the 0. Why 0? Because they're in the same direction. So in that case, the cosine of 0 being 1, and this will be true about k hat dot k hat and j hat dot j hat, will also be 1. But all the others will be perpendicular. Here's I hat, here's j hat, that's 90 degrees. So in this case, I hat dot j hat will be equal to 1 times the cosine of 90 degrees. And I think at this point, we know that cosine of 90 is 0. So all of these, j hat dot I hat and all this chart, all these are 0. And I won't belabor the point by doing that all in great detail. That's why you have notes and you have a text. So the dot product has its applications everywhere in electricity and magnet, of course, in mechanics and math methods and all the other classes you take as well. So that's the first type of a vector product. The second type is the cross product, which is defined in this manner. A cross B is equal to the magnitude of A times the magnitude of B. Instead of the cosine, we have the sine of the angle between them. And then we have a vector n hat. And n hat is perpendicular to both A and B. And really in detail, it's the plane in which A and B sit. Two lines can define a plane, so you have uniqueness. And we do this by the right-hand rule, which we take our fingers and we point it along A, and we push it into B. A is the first vector, B is the second vector. If it's been a while, A gets pushed into B and your thumb points in the direction of A cross B. N hat in this case is out of the plane of my iPad. B cross A, you put your fingers along B, please have a look at the screen, and push into A, and your thumb would be into the board. And at this point, I would ask that you please see, if you are unfamiliar with this material, or it's been a while again since you've seen this material, I have a video link in the notes in the vector section, in the vector cross product section or vector product section for Khan Academy. And I'll pause here and I'll give you time at your leisure to have a look and come back when you're ready. If you've watched the video, you saw the right-hand rule everywhere. And let's just do this chart again. Let's look at I cross j hat. I hat's in the x direction, j hat's in the y direction. We take my fingers and we point them along the I direction and I cross them into j. So it's vector that way, and I cradle it into j and my thumb points out at me. And I know that would be in the z hat direction, so that would be k hat. I cross, for example, I hat would be equal to 0 because the sine of the angle between I hat and I hat is 0. And in an undergraduate course, I would do this. I would very carefully lay all these arguments out. I would do the entire table. I hat cross I hat is 0. I hat cross j hat is k hat. I hat cross k hat is minus j hat. And then everybody would be in class moving their hands around. But for us, and I do present this in every class, you may have seen this cyclic diagram where I cross j goes into k. As we go clockwise, we pick up a plus sign. So j cross k would go into I hat. K cross I would go into this way, j hat, and so on. What happens if we have j cross I? If we go j cross I, we're going in the opposite direction. We're going counterclockwise and we pick up a minus sign. So j hat, for example, cross I hat is minus k hat. Knowing this cyclic diagram will carry you through all your cross product algebra. And we know, if you've seen it before, another way to do the cross product. I don't necessarily think this is the most efficacious way, because not everybody comes to me knowing determinants. But if you do, you can verify on your own time. This is A cross B. Okay. So the very first non-trivial operation, the very first operation that distinguishes an advanced course in electromagnetism regarding vector calculus has to do with something called the gradient. The gradient is the sort of workhorse of this entire field. So we really need to get this we really need to get the foundations set and make sure we understand the interpretation of the gradient, how it operates, and then we can extend what we know to physical law. So let's talk about the gradient. The gradient in Cartesian, we'll start with Cartesian. The gradient in Cartesian coordinates is going to be a set of partial derivatives. And for a while now, just to emphasize that it has vectorial properties, I'm going to write it this way. It's a nicely symmetric operator, partial z. And what does it do? Well, it acts on scalars. In the do what comes naturally category of mathematical operations. So if we have, for example, f of x, y, z equal to x squared y plus z cosine y grad f. And I'm going to pause here, and I would ask that you please work along with me. Take about a minute to solve that problem and come back and we'll work through it together. So in this case, we would have I hat partial x plus j hat partial y. And let's go ahead and emphasize what it is by writing it again. Acting onto x squared y plus z cosine y. Let's put that in brackets. So this will be I hat, and I start searching for anything with x, and there it is. And I will get 2xy. There's no x in z cosine y, so I move on to j hat. I look for y in this argument. I see x squared, the derivative of y is 1. And here I see plus z, and then I'll have minus sine of y when I take the derivative there. So from a purely mechanical point of view, this is quite simple. And then k hat, and I look for z. The derivative of z with respect to z is 1, and I get cosine y. Again, this is very simple. But the importance is not necessarily in just taking the raw operation with the gradient. You need to know what it means and what it represents, and let's do that now. And I'm going to move on to the second piece of tape because I would like to keep these somewhere in the range of 15 to 20 minutes per tape video.